Morning, Miss.
Um, are you seeing blinking screen?
Yes, seeing the blinking.
I think this one is this one I think because of okay sudah. Okay already? Is it okay?
Yes.
I'm trying to like try this OBS recording. That's why I think it's blinking just now. Mm, okay. Cepat, we wait for some of our friends to join us. We start in 2 minutes. Okay, I think I can start. So, good morning once again. So, today, as I mentioned yesterday in our WhatsApp group, we will cover the remaining content in chapter 2 for for our continuation from our chapter, previous lecture session. Okay, so this today we only do lecture. So next week we will meet 3 times. Um, the first session will be our lecture, and then the next session, the replacement will be the practical that we should be doing this week. And then Friday practical as usual for practical week 4. Okay. So I maybe most of you know already the recording function for part-time lecturer is not available anymore in Google Meet. So if you have a recording software at your side in your device, you can do the recording if you want. I will also try to capture the recording from my side using my software. Today is my first time trying it out. So I hope it will be okay. Okay, so can we proceed to start with our lecture? Is everyone ready?
Okay.
All right, thank you. So we will have, as usual, we'll have patuh rest in between, break in between. Okay. So let me just, I'm gonna, all right. Okay. So this is continuation of our discussion last week for chapter 2, database system. So today we will cover the remaining content for this chapter. So first, let's look at the learning outcomes we have discussed last week for the first two learning outcomes, which is the distinguish of database approach that you have, the traditional one, the traditional database and the modern database. And then we have discussed about some of the functions and components of Dbms. So today we will continue on still on component of Dbms, and then we will discuss on this three-level architecture and also the logical and physical data independence. And then the last one will be differentiating between various Dbms architecture. Okay, so first let's look at the next part of a Dbms system. So a Dbms is partitioned into several software components, or also known as module. Okay, so each of these component is assigned to a specific operation. Okay, so some of the function of the Dbms are supported by the underlying OS, operating system, but the operating system, it provides only basic services, and the Dbms must be built on top of it. So the design of this Dbms, it must take into account the interface between the Dbms and also the OS. So the major software components in a Dbms environment are shown in this figure here. So we have the Dml Preprocessor, query processor, DDL compiler, also the dictionary manager, database manager, and also the program object code. So this diagram here shows how the Dbms interfaces with other software components such as the user queries, the access method, the file management techniques for storing and retrieving records. Okay, so it's here, the application program. So this is um, one of another component of Dbms, which is the software components we have in Dbms. So Dbms interfaces with other software components such as this one, just now I mentioned, the queries, also the access method. Okay, so still under components of Dbms, we discussed in detail some of the component that we have in this system, in this Dbms. So the first one is the query processor. Okay, so query processor, this is a major Dbms component that transform queries into low-level instructions directed to the database manager. Okay, so from query processor, it will translate, it will transform queries into low-level instruction and direct it to this database manager. So the database manager here, also known as the DM. Okay, so DM here interfaces with user submitted application, program, and queries. So this DM, database manager, it accepts queries from the query processor and examines the external and conceptual scheme to determine what conceptual records are required to satisfy the query request. Okay, so and then after that, this DM will then places a call to the file manager, which is down here, to perform the request. Okay, so we look at what we have down here after this. So next, let's talk about the Dml preprocessor. This one. Okay, so this module will convert DML statements embedded in an application program from here into standard function calls in the host language. So the this DML preprocessor, it must interact with the query processor to generate appropriate code. Okay, so it must work together with this query processor so that it can generate appropriate code. Let's see this one, this arrow here showing that there's communication between these two. So next, let's look at the next component we have. So first, the first one, let's talk about the DDL compiler. So the DDL compiler, this converts DDL statements into a set of tables that contain metadata. Okay, metadata, remember metadata, data inside the data. So these tables are then stored in the system catalog. Okay, so we have discussed about what is metadata and what is system catalog in our previous lecture. So we also have the control information, which is stored in. Okay, Russell, thank you for informing. So where am I? So we have the catalog manager. Okay, the DL compiler will refer to the catalog manager. So what this catalog manager do is it manage access to and maintains the system catalog. So the catalog manager, it manages access to the system catalog and also maintains the system catalog. So the system catalog here is accessed by most Dbms components. Okay, so most Dbms components will access this catalog manager. Okay, so as you can see the arrows here, we have the query processor, database manager, also the file manager, and the DDL compiler. Okay, and then we also have this file manager here, which communicates with the Dbms components, communicate with the database manager and also the catalog manager. So what is the purpose of this file manager? So this file manager, it manipulates the underlying storage files and manages the allocation of storage space on disk. Okay, so basically this file manager is the one that is responsible to manage the storage file on the disk. Okay, so that's about file manager. So now let's look at more into detail on database manager. Okay, so inside the database manager, here so we go depth into this database manager. So under database manager, we have authorization control, and then we have command processor, integrity checker, also the query optimizer, and then the transaction manager, then the scheduler, recovery manager, and also the buffer manager. Okay, so let's discuss each one of these. So the first one is, let's talk about authorization control. So this module, authorization control, will confirm whether the user has the necessary authorization to carry out the required operation. So from the query processor, so in this in authorization control here, it will determine, or it will authorize the operation or the request that is requested by the user. Does this user has the necessary authorization to proceed with the operation that is requested? Okay, so it authorizes if the process can proceed. And then it goes to command processor. So once the system has confirmed that the user that requested the operation previously in this from authorization control, if it's confirmed that this user has the authority to carry out the operation, the control is passed to this command processor and it will process the command. So if it goes to the integrity checker, so it will go to the integrity checker for an operation that changes the database. So the integrity checker will check whether this requested operation satisfy satisfies all necessary integrity constraints, such as key constraints. So this integrity checker will check whether the requested operation follow or it satisfy the necessary integrity constraint in the query. And then for query optimizer, this module will determine an optimal strategy for query execution. Okay, so when we type our query, our SQL command in our SQL class, so this query optimizer determines the optimal strategy for executing the query that is given to the SQL class. And then for transaction manager, so this transaction manager, this module, it performs the required processing of operation that it receives from transaction. Okay, so if it's the query is for transaction, this module will perform the required processing. So it depends to the query that is given to the command processor. And then scheduler. Okay, so this scheduler, this module scheduler is responsible for ensuring that concurrent operations on the database proceed without conflicting with one another. So what it does that is that it controls the relative order in which transaction operations are executed. So the scheduler here, it ensures concurrent operation proceed or happen without conflict with one another. Okay, so the operation must go one by one. It cannot conflict with other query. So the scheduler will handle the scheduling for the operation to go through this system. And then we have the recovery manager. After scheduler, we have the recovery manager. So this module, this recovery manager, it ensures that the database remains in a consistent state in the presence of failures. So if there is failures, this module will ensure the database will be in a consistent state even if there is a failure. So it is responsible for transaction commit and abort. Okay, a commit and abort. It's responsible for these two transactions, commit and abort for this recovery manager. Yeah, and then the last one we have in this database manager is the buffer manager. So this one is responsible. This module is responsible for the transfer of data between main memory and secondary storage, such as disk and tape. So the recovery manager and the buffer manager here are sometimes referred to collectively as a data manager. Yeah, so these two usually called as data manager, buffer manager and also recovery manager. So the buffer manager is sometimes also known as cache manager. Okay, so another name for this buffer manager is cache manager. So this is the full view of a database manager in our Dbms. Okay, so that's it for the components of Dbms. So now we will discuss on this architecture, the ANSI SPARC architecture. So this architecture stands for American National Standard Institute Standard Planning and Requirements Committee architecture. So this is an abstract design standard for Dbms. So it was proposed in 1975. So this architecture, it recognized the need for a three-level approach with a system catalog. So most modern commercial DBMS are based on this standard three-level architecture. So like we will look at the architecture here. This is the example. So we have the external view, external level, and then we have the conceptual, and then we have the internal view. Okay, so the first one is external level. So this architecture, it identifies three level of abstraction, that is three distinct levels at which data can be described. And then let's go to the first level, external level. So the way user perceive the data is called the external level. So this is the user's view of the database. Okay, so these are the users, and the external level or the external view is the view that what the user can see on the system. So it describes that part of the database that is relevant to particular user. So this user here can see view 1, user 2 here can see view 2, and so forth. So this user can only see what this user is authorized to see. So the conceptual level, it provides both the mapping and the desired independence between external and internal level. Okay, so it describes what data is stored in the database and also the relationships among the data. So this is the community view of the database here in the conceptual level. So the way the DBMS and the OS perceive the data is here at the internal level. So this is the physical representation of the database on the computer, which it describes how the data is stored in the database. So basically the internal level will deal with the actual database, here. Okay, so this is what we call the three-level architecture. We have the external view here, and then we have the conceptual level, and also the internal level. Okay, so I repeat, for external level, it's the user's view of the database according to what they can view, according to what they are allowed to see. And then we have the conceptual level, the community view of the database, which here will give you what are the data stored and the relationship amongst the data. And internal view is where this is where the physical representation happen of the database on the computer. So this will show you how data is stored in the database. Okay, so let's look at this example here. So we have the view 1. Okay, so this external view and conceptual view and internal view. So we have this is user 1, and then this is user 2. So they have different things or different entity that they can see in this database. Okay, so and then at the conceptual view, it actually combine these two view into this one. So if you can see here, the new thing that you can see in this conceptual level is the date of birth. Okay, so from external view 1, the S number is referred to staff number in this conceptual level. And then we have the internal level. So these are how this shows you how the data is stored in the database. Okay, so you have the staff number, the branch number, the first name, the last name, the DOB, the salary, and also how you store the data in this database. Okay, so this is just an example on how this three level of Ansi sparc, Ansi sparc architecture in Dbms. So these are the data that is stored in database. These are the views of the external view, and this is what happened in the internal level. So now let's look at the objectives of this three-level architecture. So the objective of this three-level architecture is to separate each user's view of the database from the way the database is physically represented. Okay, so each user, they should be able to access same data, but of course they can have a different customized view of the data. And then next is each user should be able to change the way he or she views the data, and this change should not affect other users. Okay, so in other words, the user's view is immune to changes made in other views. So let's say this user one change its view, it will not affect the view of the rest of the user that is using the same database. So user should also not have to deal directly with the physical database, especially the storage details, such as indexing or hashing. So in other words, a user's interaction with the database should be independent of storage consideration. Okay, so these are the objectives of the three-level architecture. Still have more. So the next one would be the DBA, the DBA Database Administrator. This DBA stands for Database Administrator. This DBA, they should be able to change the database storage structure without affecting the user's view. So the internal structure of the database also shouldn't be unaffected by any changes that happen to the physical aspects of storage, such as the changeover to a new storage device. Okay, so if like there is a replacement of a storage device, it should not be affected by this internal structure should not be affected by the changes of a new storage device. And then another objective of this three-level architecture is that the DBA should be able to change the conceptual structure of the database without affecting all users. So any changes happen should not affect all the users that they have in this DBMS. Okay. Take 5. We take 5. Take 5, yeah.
Okay.
Okay, can we continue?
Yes.
Okay. So this is the previous view, the previous figure that that we have in the previous slide. So this shows you the differences between the three levels. Okay, so we have the external view, and then we have the conceptual level, and also the internal level. So the two different external views of staff exist in this DBMS. So one consisting the first view V1 consists of the staff number indicated as SNO, and then we have the first name indicated as F name, and then we have the last name indicated as L name, and then the age and salary. So the second view we have here, external view second, we have the staff number indicated as staff NO, and then the last name indicated as L name, and the number of the last branch the member of staff works at, which indicated with a branch number. Okay, so this branch number is referring to the branch of the member of staff works at, this one indicated as branch number. So these external views, these two external views are merged. Okay, it is merged into this one conceptual view. Okay, so it becomes the conceptual level. So in this merging process, the major difference is that the age field, okay, the age field has been changed into a date of birth field, the DOB, if you notice here, as I mentioned previously. So the age here, it is changed to date of birth. So the DBMS here, it maintains the external or this conceptual mapping. For example, it maps to the from this external view as staff number to the conceptual level. It maps to this field here, and then also similar to the rest, like last name, first name, it maps to some of the field that is available in the conceptual record. So this conceptual level here is then mapped to the internal level, which contains a physical description of the structure for the conceptual record. So from the fields that we have in the conceptual level, it is indicated in the internal level with a physical description. So at this level, at this internal level here, we see a definition of the structure in a high level language, yeah, which is this language. So the structure contains pointer, it contains next, which allow the list of the staff records to be physically linked together to form a chain. Okay, means this language here next, it points to the next staff record. So note that the order of fields at this internal level is different from what we have in conceptual level. Again, the DBMS will maintain the conceptual to internal mapping. Okay, if you see the order is not the same. Okay, like here we have integer, staff number, and then branch number, and then first name, last name, right? But here at the conceptual level, it doesn't follow what this internal level, it doesn't follow the sequence at what we have at the conceptual level. Okay, but still it still maps from the conceptual level to the internal level. The difference is that there is a high level language which is assigning what type of data is that in the database. Okay, so this is an example of three-level architecture in Dbms. So we also have indexes for staff. So this one, it defines indexes for staff in this database. Okay, so there is also a major objective of this three-level architecture. It is to provide data independence. Okay, so which means that upper levels are unaffected by changes at the lower level. So there are two kinds of independence. There are two kinds of data independence here in this three-level architecture. We have the logical data independence, and then we have the physical data independence. So let's look at the three different types of schema that we have in this database. So we have the external schema, yeah, and then the conceptual schema and the internal schema. Okay, so at the highest level here, we have multiple external schema, also known as sub-schemas, that correspond to different views of the data. Okay, so this is the view. Each schema will have different view. And then at the conceptual schema here, at conceptual level, we have this conceptual schema which describes all the entities, the attributes and relationships together with integrity constraints. Okay, so remember in conceptual schema, we can see, or we will know the relationship, we'll be able to see the relationship and also the integrity constraint in our database. And then next we have the internal schema. So in this, at the lowest level of abstraction, we have the internal schema. So this is where the complete description of internal model will be presented. It contains the definition of stored data, the methods of representation, the data fields, also the indexes and storage structures that is used. Okay, so there is only one conceptual schema and one internal schema per database. Okay, so every database will have multiple external schema, but only one conceptual schema and one internal schema. Okay, so we have the logical data independence, and we have the physical data independence. So the logical data independence is between external schema and conceptual schema, and the physical data independence is between conceptual schema and internal schema. So here is where the external conceptual mapping will happen, and at the physical data independence is where the conceptual and internal mapping happen in our database. Don't know. Give me a sec. Okay, so here is the details of the differences between logical data and physical data independence. So the logical data independence, it refers to the immunity of external schemas to changes in conceptual schema. So changes to the conceptual schema such as addition or removal of new entities, if these changes happen in the conceptual level, also maybe removal of attributes or maybe new relationship established, it should be possible without having to change the existing external schemas or having to rewrite the application programs. So this is what we refer to a logical data independence. And then we have the other one, the physical data independence. So here is where the immunity of conceptual schema is referred to, whereby if there is a changes in the internal schema. Okay, so changes to the internal schema, such as maybe, for example, like using different file organizations or storage structures, or maybe using different storage devices, or maybe there is a modification of indexes or hashing algorithms. It should be possible without having to change the conceptual or external schemas, right? So from the user's point of view, the only effect that may be noticed is the change in performance. Okay, so any changes that happen in your internal schema, usually, typically, the major differences that always noticed by the user is the performance. Okay, so these two are the type of independence that we have in Dbms structure. Okay, so now we are at multi-user Dbms architecture. Before we proceed to this one, we take a break. Okay.
Okay.
10 minutes break. Okay, I'll be back in 10 minutes time. Thank you. Okay, can we continue?
Okay.
All right. So now we are at the next part of this lecture, which we will be discussing on several architecture, other common architecture that are used to implement multi-user database management system. So we will discuss on teleprocessing, file server, and client server. So some of these might be familiar to you already, like client server. I think all of you are familiar with this architecture already. Okay, so let's look at the first one, which is the teleprocessing. Okay, so this is the traditional architecture for multi-user system where there is one computer, typically this one, um, with a single central processing unit with one CPU and a number of terminals. Okay, so these are the terminals connected to this desktop. Um, so all processing in this architecture is performed within the boundary of the same physical computers. Okay, so these user terminals that we have here, okay, they are typically like dumb. Okay, it's labeled as dumb because it's incapable of functioning on their own. Okay, so all are cabled to this central computer. So everything in this Dbms will always refer or will always depend on this one one computer here in the with this single CPU. So what happens is that the terminals here, it will send messages via the communication control subsystem of the OS to the user's application program, which in turn uses the services of DBMS. So in the same way, the message will be routed back to the user's terminal. So there's every time these terminals want to request from the database, it will go to this one particular database, and then this central computer will provide the service to the terminal. So this architecture, it places a tremendous burden on this central computer, which had to not only to run the application program and the DBMS, but it also carry out a significant amount of work on behalf of all these dumb terminals. Okay, so in recent years, there have been a significant advances in the development of high performance personal computers and networks. So there is now an identifiable trend in the industry towards downsizing, that is referring to replacing expensive mainframe computers with more cost-effective networks or of personal computers that achieve the same or even better results. Okay, so this trend has given rise to the next two architectures. We look at file server first, and we will discuss on client server after this. Okay, so the file server architecture is where a computer to a network with the primary purpose of providing a shared storage for computer files such as documents, spreadsheets, images, and databases. So in this file server environment, the processing is distributed about the network. Okay, it is depending on this local area network. So the file server that we have here, it holds the files that's required by the application on the DBMS here. Yeah, so however, the applications and the DBMS run on each workstation. Yeah, the DBMS will run on each workstation and request files from the file server through the LAN when necessary. Okay, so all these workstation, um, if the application and the DBMS run on this workstation, and then it will request for data from the file server when required or when necessary, and the files will return back to the workstation through this local area network. So in this way, this file server architecture acts simply as a shared hard disk drive, right? So the DBMS on each of these workstation sends requests to the file server for all data that the DBMS requires that is stored on disk. So this approach can, of course, generate a significant amount of traffic, which can lead to performance problem. Okay, because all these workstation, maybe there's more. Here only shown to you is 3 workstation. So if there's more workstation and keep requesting to this file server, there can be a traffic overload, which can proceed to give a performance problem in this local area network. So these are these advantages of this file server architecture. There is a large amount of network traffic, as I mentioned just now, and a full copy of the DBMS is required on each workstation, which which um, which we know that if this happen, like every station has the full copy of the DBMS, it will use up the storage on each workstation. And the last disadvantage for this architecture, it's the concurrency, the recovery, the integrity control is more complex because there can be multiple DBMS accessing the same files. Yeah, so like workstation 1, workstation 2 is accessing the same file. So this can affect uh, the concurrency, the integrity control on the DBMS. Okay, so due to these disadvantages, we have another architecture that is client server. Okay, so we have this traditional 2-tier client server. So to overcome the disadvantages of the previous architecture, the teleprocessing and the file server architecture, this client server architecture was developed. So as the name suggests, there is a client process, okay, at tier 1. Tier 1 first tier is the client process, which requires some resources, and then the server at the second tier, which provides the resources to the first tier. Yeah, so there is no requirement that the client and server must reside on the same machine. So there are many advantages to this type of architecture. For example, like it enables wider access to existing databases. It also increases performance, the overall performance. Also, hardware costs may be reduced as well. And like because the previous one, the file server, you need to have more than one workstation. And then communication costs also reduce, and it also increase consistency. Okay, so the first tier here, where the client is, it provides the user interface, and this is where the main business and data processing logic happen. And then at the second tier, the database server, it provide the server-side validation and also the database access. So now let's look at this summary of client-server function. So we have the client, it manages the user interface whereby the server, it accepts, processes database and processes database requests from clients. And then the client will accept and check syntax of user input through the user interface. And then the server will check authorization. And then at the client side, it processes the application logic. And at the server, it will ensure integrity constraint not violated. The client side, it will generate database request and transmit it to the database server. So the server will receive the request, and it performs query or update processing and transmit response back to the client. And then the server will also maintain system catalog. It provides concurrent database access and also provide recovery control. So the client will pass response back to the user, right? So these are the summary of this client server function. I think this one is very straightforward. So this is the traditional client server architecture. We have 3-tier client server. Give me a second. Sorry. So we have this 3-tier client server. We have the first tier, the client, and then we have the second tier, which is the application server, and the third tier database server. So the need of enterprise scalability due to a scalability challenge, the 2-tier client server model is upgraded to this 3-tier client server. So as applications become more complex and could potentially be deployed to hundreds or thousands of end users, the client side presented 2 problems that prevented scalability. Okay, so a fat client, a fat client which require considerable resources on the client's computer to run effectively. So this includes disk space, RAM, and also CPU power, and also a significant client-side administration overhead. So that's why we have this three layers of this client server. So the first layer is the user interface layer, which is the first tier, so which runs on the end user computer. Okay, so this is the end user, the first tier. And then we have the application server here, where the business logic and data processing layer. This middle tier, it runs on a server and known as application server. And then the third tier, the Dbms, which stores the data required by the middle tier. So this tier may run on a separate server called database server. Okay, so you have the client, go to the application server, and go to the database server. So as illustrated in this figure here, the client is now responsible for only the application's user interface and perhaps performing some simple logic processing, such as input validation. So here is where we call this client as a thin client. Okay, so this first tier is the thin client, which only provide user interface to the user. Okay, so every time this thin client is used, it's actually accessing the application server, and then we'll go to the database server if required. So this 3-layer, or 3-tier client server, it can run on a different platform as well. So let's look more into this three-tier client server. So there are advantages of this design. So then the need for less expensive hardware because thin client only thin client is required for this architecture. And then the application maintenance is centralized with the transfer of the business logic for many end users into a single application server. So this will eliminate the concerns of software distribution that are problematic in the traditional two-tier client server model that we discussed earlier on. And also, it's easier to modify or replace one tier without affecting others. So it makes it is easier to modify any tier if there is a need without affecting the other tier. And then load balancing is also easier with the separation of the core business logic from the database function. So an additional advantage is that the three-tier architecture, it maps quite naturally to the web environment. So this one is with a web browser. The web browser can act as the thin client and the web server acting as the application server. Okay, so these are the advantages of this three-tier client server architecture. Okay, so this is an example of a three-tier client server. So this one is taken from this ebook. You can refer to this ebook for more description on this figure here. So we have the thin client here. We have the browser, at the accounts payable processing, and then we have a cash flow analyst, and we have a customer service representative. Okay, so they are accessing the application or the web server through browser. So this user here, it access the database of vendors, the purchase orders, the PO, and also the vendor invoices. As for this user, it access the database of customer receipts and payments to vendor through the application server, through browser as the interface. And then we have the customer service representative accessing browser through this iPad, through this tablet, accessing the application or the web server. So here at the application tier or the web application tier, it provides the AP, account processing, account receivable, the order processing, inventory control, also access and connectivity to this Dbms, and also the dynamic web pages, and also management of sessions. So at the enterprise tier here, this one is where the Dbms is located. Okay, so you have the transaction databases which contain all organizational data or summaries of data on department servers. So that's three-tier architecture, a three-tier client server architecture. So the three-tier architecture, it can be expanded to these n tiers with additional tiers that is providing more flexibility and scalability. So for example, as illustrated in this figure here, the middle tier of the architecture, it's split into two, right? So you can have the web server as one tier, and you can have the application server as one tier, another tier. So this application, in this case, the application server will host an application programming interface, the API, to expose business logic and business processes for use by other applications. So an application server, it must handle number of complex issues like concurrency, network connection management. It also provides access to all the database server and also provide database connection pooling, legacy database support. It also provides clustering support, load balancing, and also failover. Okay, so those are the number of complex issues that will be handled by this application server. So basically, the client here will access the web server. So it's required if the client required any services from the application server or the database server, it will go through the web server. And then we have another this complex application which often built on the top of several resource managers such as Dbms or operating system or user interface. So this is the TP, also known as transaction processing monitor. So it forms the middle tier of the three-tier architecture. It's located here. So this TP monitors, it is a middleware, which it's a middleware component that provides access to the services of a number of resource managers and provides a uniform interface for programmers who are developing a transactional software. So this TP monitor, it forms the middle tier, this one here, of the three-tier architecture. So a program that controls data transfer between clients and servers in order to provide a consistent environment, particularly for online transaction processing. Okay, so OLTP. So this TP monitor, it controls the data transfer, so, particularly for this OLTP. So we have here, it shows you where the TPM is situated. It's between tier 1 and tier 2. Okay, so this application server, it's with the TP monitor. Okay. And then the last one. So this is this Dbms. So we have Dbms. So it's a distributed database management system, which consists of a single logical database that is split into a number of fragments. So each fragment is stored on one or more computers, or also known as replicas, under the control of separate DBMS. Okay, so this DBMS, it's interrelated collection of shared data physically distributed over a computer network. So a given site may have a local copy of all, part, or none of a particular database. So this DBMS, it permits the management of the distributed database and makes the distribution transparent to all users. So this DBMS, it has several characteristics. So number one is its collection of logically interrelated shared data, this one. Fragments in the database, it may be replicated. So sites are linked by communication network like this. We have site 1, site 2, site 3, site 4. It's linked by this network. And then data at each site is under the control of a DBMS. Okay, so one DBMS will be controlling the data at each site. Site 1, it will have its own database. Site 2 has its own database, and so forth. So DBMS at each site, it will handle local applications, and each DBMS will participate in at least one global application throughout this um, for example, like in this figure here. Okay, so this is another type of DBMS, the DBMS. So depending on the organization, which which architecture they want to use, but typically the most used one is the three-tier client server architecture. So that's about it for this lecture. So thank you so much for your attention. Do you have any questions?
No question.
Thank you, Christian, for now. Okay. So, okay, thank you. I noticed from the practical one, practical two, not all have submitted, not everyone submitted the homework. So I really hope that you can help me to help you because I really need to know your level of understanding on the practical part. So some of you have submitted. Thank you so much for your submission. Most of you have not submitted yet, not even half submitted. So I hope I can see a submission by this week. I give you this week you have two submissions to do, um, practical one and practical two. So I have not put any submission for practical three. So before we proceed to PLSQL, I would really like to see your understanding on the previous practical so that I know what your level is and so that I know how to help you in the future. So please help me to help you, help yourself also. If you like don't understand what to do, please let me know. Don't keep quiet, okay? So if you have no more question, um, we can we can we'll dismiss the class. Not yet. Don't leave the session yet. Leave the session at 10:45. Can you do that?
Okay.
Okay, so those take this time to check again your practical and please do submission if you don't if you have not done it yet. So for practical, I think I already guide you, okay? But if you still don't know what to do or if you still have problem with your SQL Plus or your installation of your Oracle 21C, please let me know, okay? I should see you in like 1 week time, face to face. So I hope during face to face, maybe you want to keep your questions, or maybe you want to tell me like face to face you don't understand. Maybe you can do that also, but I would appreciate if you can WhatsApp me personally if you are shy. WhatsApp me personally and let me know what's your problem with the practical. Okay? So I think that's all for today. Please don't left the session yet. You can left 10:45. Thank you so much, everyone.
Okay, miss. Thank you.